In this lesson, we're going to talk about direct variation. Direct variation is a relationship between two variables in which one is a constant multiple of the other. When one variable changes, the other changes in proportion to the first. Here you can see the formula for a direct variation, y equals kx. This is another formula that will not be on your final formula sheet for standardized testing. So this is one of those formulas you do want to commit to memory. So as you can see, it looks a lot like other equations that we have been talking about, or other formulas, where we have a y and an x, and that just represents a coordinate, so a coordinate xy. Now, the k variable, this is going to be something we like to call the constant of variation, better known as the slope. Let's look at an equation here to the left and see what it looks like graphically. Here we have the equation y equals 1/3 x. So you can see we have the y and the x, and you can see that we have that constant of variation, or the slope of 1/3. So what you can notice here that might be familiar to you is if we were to relate it to the slope-intercept form of an equation. Slope-intercept form of an equation is y equals mx plus b. What this problem is missing is the b component. B in a direct variation is always going to be 0, which means that our graph is always going to go through the origin. So as you can see here, our graph not only goes through the origin, but it also has a slope of 1/3. Just as a reminder, and just to say it again to emphasize it, direct variation equations, they always pass through the origin. Okay, let's go ahead and look at direct variation just a little bit deeper. All right, sometimes we're given tables of values and we're asked to determine whether this table of value creates a line that in turn is a direct variation equation. So, one way to look at it is to see if that line goes through the origin, because most likely, if it's linear at least, if it goes through the origin, it is a direct variation. But just because it goes through the origin doesn't mean that it's linear. So let me show you a way to always detect whether or not it is direct variation. So you can see these two examples at the top are indeed direct variations, which means they're graphs and the line goes through the origin and has a constant slope. But let me show you how to determine this. I'm going to use the formula that I have here up at the top right hand corner. Y equals kx. Now, what is common is the k. The constant of variation of the slope is going to be the same number. Watch what I'm going to do here, and you'll see why I'm going to do this in a second. I'm going to take this formula and I'm going to solve it for k. So what I'm going to do is I'm going to divide both sides by x. That will eliminate my x's over on the right side, and that will give me y divided by x is equal to k. So essentially what I have is that constant of variation equals y over x. I'm going to use that right there. All I did was I manipulated the original formula around to solve for k. So I used those literal equation skills. Now what I want to do is I want to figure out which one of these tables has a slope that is y over x and it's all the same. Let me show you what I mean here. So you can see that in each of my, in my table of values, I have an x and I have a y. So let's go ahead and solve for k for each of the pieces here. I'm going to divide y divided by x to give me my k value. You'll see in the first one, -18 divided by -3 is going to give me 6. -12 divided by -2 is going to give me 6. And I'm just going to continue on, and you can see that they're all 6, except for this one right here. You can see for this one, it's 0, 0. And we know 0 divided by 0 is not going to be 6. But we do know that this creates a direct variation. Let's continue on. K is equal 6. and k is equal to 6. Because my constant of variation, or my slope, is the same all the way down the list, and it just so happens to go through the origin, this is indeed a direct variation. All right, let's go ahead and look at the other one. I'm going to do that same thing where I take y and I divide it by x. You can see here that my k value is -3. K is -3, and it just so happens that k is -3 all the way down. Although k is -3 all the way down, it doesn't necessarily indicate that it's going through the origin. That's okay. As long as this is occurring, we can say that this is a direct variation equation. Okay, non-direct variations. So we're going to do that same exact concept where we divide the y by the x. You can see here, -20 divided by -4 is going to give me 5. And then -10 divided by -2 is 5. Uh-oh. -6 divided by 0. Well, that's actually undefined. 5 divided by 1 is 5. 16 divided by 3. Yikes, that's a decimal. That's actually going to be 5.33 repeated. And then 20 divided by 5 is 4. As you can see here, my constant of variations are all over the place, and therefore making this not even close to a direct variation. Same idea for the last one, y divided by x. So we do see that it goes through 0, 0. So that actually says that, oh, this could be a direct variation, but we have to do the other test. 1 divided by 1 is 1. 4 divided by 2 is 2. At this point, we can stop. We don't even need to go any further because we can see that they do not equal. The constant is not the same. Therefore, it is not a direct variation. Okay, now let's go ahead and graph it. Now, this should be really familiar to you because we've already done this before. But we're going to go ahead and graph this, and we're going to use a table of values to do so. Now, actually, there's two ways to do it. I'm going to show you the table of values, and I'm going to show you just graphically how you would do it. So let's go into our graphing calculator and go to y equals. And right next to y sub 1, let's place 2x. And go to your table of values by pressing second graph. And go ahead and grab some nice points that will fit right on our coordinate plane here. I'm going to go ahead and use -2 and -4. I'm going to go ahead and plot him. Put a nice dot there. And I'm going to do -1 and -2. And then I'm going to do my origin, because direct variations always go through the origin. And then I'm going to do 1, 2. And then the last one I'm going to do is 2, 4. Perfect. All right, you can see that it goes right through the origin and it creates a linear equation. So I'm going to go ahead and draw a nice straight line through those dots with my arrows at the end. All right, so that's using the table of values. The other thing I could have done to simplify this and to graph it would be just to look at the equation. I can see that my slope is 2. And I can see that my y-intercept is 0 because it doesn't have anything being added or subtracted next to it. So therefore, I could immediately take my y-intercept and graph it. And then from there, find my rise over my run, which would be 2 over 1, plotting all of those points. So I could either go directly from the equation or I could create a table of values. Either or is perfectly fine to graph a direct variation. Okay, I'm going to show you 2 application problems of direct variation to kind of show you what we use it for. Here it says, determine the values of the unknowns. Y varies directly with x. If y equals -4 when x equals 2, find y when x equals -6. So you might be thinking, well, I could set up a proportion for this. Well, you could. That's basically what we're going to be doing. But let me show you how to actually set this one up. The first thing you notice is that it says y varies directly with x. When you see something like that, you want to immediately write down the formula y equals kx. Because in a little while, we're going to be learning about inverse variations, and it has a different formula. So you want to make sure you write down the correct formula. Okay, now what we're going to do is we're going to use the given information. It says that we're given that y equals -4 and x equals 2. When I'm given 2 variables and I have a third one to solve for, that's what I'm going to do. I'm going to substitute those numbers using the substitution property into my formula to solve for the third. So let's go ahead and do that. I'm going to substitute -4 in for y. K, I'm going to leave exactly the way it is, and I'm going to substitute 2 in for the x. Now, let's go ahead and solve for the unknown. I'm going to divide both sides by 2. Notice how I'm showing my steps. Therefore, my k value is going to be -2. This right here is my constant of variation. That's not answering my question quite yet. Now what I want to do is I want to use this k value and I want to find my missing information. It says now find y when x equals -6. So I want to find y when my k value is -2 and my x value is -6. So I just substituted my new givens to find my new unknown of 12. Now y equals 12 is the answer to my question because the original question was saying find y. And there it is. All right, here's another application problem, but this one actually, it's very similar to the top one, but now we actually have a situation occurring. It says the total cost of filling up a car with gas varies directly with the number of gallons of gasoline you purchase. If 7 gallons of gas cost $15.75, how many gallons could you purchase for $45? Again, you might want to use proportions for this type of problem, but I'm just going to set it up this way just to kind of show you the math that's behind it and what's happening. The first thing you want to look at is the first sentence. Do you notice how it says the total cost of filling up your car with gas varies directly with the number of gallons of gasoline. So that means that we are going to automatically know that we're going to be using y equals kx. And I'm actually going to change my variables. I'm going to call the c cost. The k is going to remain the k, and the x is going to be the gallons. Now you can see that I placed those in the proper locations because it's saying that the first thing is the total cost, and that thing is the thing that's varying directly with the number of gallons. That's the thing that's changing. So I'm going to place that next to the number that's changing, my slope. Now I'm going to go ahead and use that equation and substitute my first set of given information. So C equals kg. I'm given that 7 gallons of gas costs $15.75. So I'm going to say $15.75 equals K times 7. And you can see what we're going to do here. We're going to go ahead and divide both sides by 7. Feel free to use your calculator to calculate this. But my K is going to be 2.25. Okay. Now, that's not my answer because I do need to answer the question. How many gallons, that's what I want to know, could you purchase for this cost? So, if $45 is my cost, I know my K value is 2.25. I want to know how many gallons. And I'm just simply solving that one-step equation. Divide both sides by 2.25. And then go ahead and calculate that. G is going to equal 20, which means it'll take 20 gallons. And that's your final answer. All right, those are some application problems using your direct variation. The big thing to remember about direct variation is that when graphing it, it always goes through the origin, which means that you do not have a y-intercept. Well, at least you do, but it's just 0.